Hi everyone, I'm Ronaldine Smi Marquez, and my report for Bridge Engineering is all about the design of compression members. So what is design of compression members? A critical aspect of the design of highway bridge piers in the design of compression members. Examples, columns in a column bent pier. In general, the design of reinforced concrete elements is covered by Section 8 of the AASHTO standard specifications. So it is beyond the scope of this text office detailed analysis of all the aspects of the AASHTO code which applies to the design of pier components. We shall, however, focus on the design of compression members as set forth in AASHTO. So, load factor design considerations. So what is it? In AASHTO standard specification, a compression member is based on the equation set forth in AASHTO 8.16.4 and 8.16.5 for load factor design. Their specifications define the axial load strength of compression members. The axial load strength will vary depending on the type of reinforcement present, and the type of loading the member is subjective to compression or pure flexure. If the effects of slenderness apply to the member, then the maximum factored moment is magnified to account for these effects. The axial load strength of a compression member is based in large part on the following parameters. So, what is it? The strength of concrete used, the yield strength of reinforced present, the gross section area of the member, the total area of longitudinal reinforcement, the confinement provided by the lateral reinforcement. So the general requirements for the design of compression members are given in AASHTO 8.16.4 1.2. The criteria governing the design compression members under pure compression are given in AASHTO 8.16.4 2.1. For those members under pure flexure, the reader is referred to AASHTO 18.16.4.2.2. So number 2, load and resistance factor design considerations. So in AASHTO, LRFD specifications, the equations for computing the compression member strength are the same as these in the AASHTO LFD provisions. So refer to AASHTO LRFD 5.7.4.4 for axial resistance and 5.7.45 for biaxial flexure strength. So the transverse reinforcement in the pier column should meet the minimum requirements of AASHTO LRFD 5.7.4.6 to ensure that sufficient confinement is provided for the concrete. In seismic zone 2 and higher areas, additional transverse reinforcement is required to enhance the column's ductilities. So number 3, slenderness effects. So when a compression member's cross-section dimensions are small in comparison to its length, the member is said to be slender. Whether or not a member can be considered slender is dependent of the magnitude of the member's slenderness ratio. So the slenderness ratio of a compression member is defined by the following expression. So KL over R, K is effective length factor for compression members, L unsupported length of compression member, and R is radius of gyration. So number 3, so it is the compute stiffness of the pier. In a process similar to that performed for the abutment in design, example 4.1, step 6, we will compute the stiffness of the pier. This stiffness will be computed for the pier subjected to earthquake motion in both the longitudinal and transverse directions. So the reader should keep in mind that it is the transverse section of the pier with respect to the bridge proper, which resists longitudinal earthquake motion, and the longitudinal section with respect to the bridge proper that resists transverse earthquake motion. So as we saw before in the abutment, a unit load of 1 is applied to determine the deflection of the resisting section. The inverse of this value yields the stiffness. The calculation for the modulus of elasticity for the concrete used 3000 psi strength was shown earlier in step 6 of design example 4.1. Once the deflection under the unit load is calculated, the inverse of the deflection is the stiffness resisting longitudinal earthquake motion. So here is the effective length. Effective length of a column is defined by the product KL and is used to determine the allowable compression in a column. The effective length factor K is the ratio of the effective length of an idealized pin-ended column to the actual length of column with various Zen conditions. The product KL represents the length between inflection points of a buckled column. So restraint against rotation and translation of column ends influence the position of the inflection points in a column. Theoretical values of the effective length factor K are presented in figure 4.13 because the column end conditions rarely comply fully with idealized restraint against rotation and translation. So the recommended values are higher than the idealized values. So columns in continuous frames which are unbraced. So by adequate attachment to shear walls, diagonal bracing or adjacent structures depend on the bending stiffness of the rigidly connected beams for lateral stability. So the effective length factor K is dependent on the amount of bending stiffness supplied by the beams at the column ends. If the amount of stiffness supplied by the beams is small, the value of K could exceed 2.0. The design values of K for riveted and bolted truss members is 0.75. For pin connections in truss members, the design value is 0.875. Pin friction. So, there. So, compute load due to longitudinal motion. Similar to the operation performed in step 7 of design example 4.1, we now compute the load acting on the pier as a result of longitudinal earthquake motion. Here, however, we take the properties of the center's 63.0 feet span in loading the piers. So, the length variable L and unit weight of deck W will be determined different from before. So, note, the earthquake force from superstructure is transferred only to the fixed bearings. In this case, only center span load is transferred to the pier in the longitudinal direction. In the transverse direction, however, we assume all bearings are restricted, guided bearings. So the diagram in the accompanying calculation sheet illustrates the bridge under longitudinal earthquake loading with the static displacement depicted at the pier location. In this calculation sheet, we determine the value of the alpha single mode factor. So here it is. So we compute the displacement, and Vs with Ps is equals to 1. So we got 1.714 times 10 to the power of negative 3 feet. And compute single mode factors. So it is 0.1080 feet. So, compute load due to transverse motion. The computation of the load due to transverse motion is similar. So, for the sake of brevity, we will skip the hand computation of this value. Note that half of the force from the end span and half of the force from the center span will act on the tire. So, assume all bearings are fixed transversely. So, we got Vy, we got tire column, So, compute load due to transverse motion, So, we will skip this step for the sake of brevity. So, Vx is equals to 123.65 K. Includes response modification factor of R is equals to 5. So, summarize loads acting on tire column. So, the part of the moment acting on the column contributed by longitudinal earthquake motion is shown. The moment resulting from transverse earthquake motion and the worst case axial load on a single column were determined using a computer structural analysis software package. A check of load case 2 produce a lower value, so load case 1 controls. So the tire column, so here is the case 1 and the 100% longitudinal motion plus the 30% of transverse motion. So here, so all in all, a check of load case 2 produces a total moment of 204 feet K, so load case 1 controls. So check for effects of slenderness. We need to determine whether slenderness effects need to be taken into account for the tire columns. So, a check needs to be performed for a column subjected to both transverse and longitudinal earthquake motion. First, the unsupported length of the column is determined and the radius of gyration calculated. Recall from section 4.24 part 3 equation 4.2.3. The radius of gyration varies for members with circular and rectangular cross sections. So the difference between the response of the tire under the two loading conditions will be defined by the effective length. So factor K used under transverse earthquake motion, longitudinal tire direction. The column is free to translate but fixed against rotation under longitudinal earthquake motion. So the column end is free to rotate and translate. So by equation 4.25, the limit for the slenderness ratio of a compression member not braced against sideways is 22. We need to consider slenderness under longitudinal earthquake motion. So, compute moment magnification. To compute the moment magnification factor, we first need to compute several parameters. The first is the beta factor, defined to take into account the effects of creep. The total dead load moment was given earlier in step 6. Its value was determined from a computer analysis of the tire frame. So next, we need to determine the gross concrete section moment of inertia. This value is used to determine the flexural rigidity of the column. We will use the more conservative equation for this. So the critical buckling load is computed using the effective length factor of 2.0 found earlier in step 7. This value is based on the tire being subjected to longitudinal earthquake motion. Finally, the moment magnification factor is computed using the criteria defined in AASHTO 8.16.5.2.7. See also equation 4.33. So the tire columns are not braced against sideways in the longitudinal directions. So you will see the step 8 compute moment magnification factor.